Now we're getting to the bulk of the lesson here. We're going to solve the system, which is 2 equations. Remember, 2 or more equations make a system. Not by graphing anymore, but by substitution. Now, these are a little bit more complicated questions, so much so that I want you to not be writing down with me. I want you to put your pencils and highlighters down. I want you to watch me solve this system by substitution, and then I'll give you a chance to write it all down. But if you're trying to write and listen at the same time, it's not going to work. So watch it happen. The first step to solve a system by substitution is to isolate one of the variables. What did we mean by isolate just a second ago? Make it by itself. So let's look at our system we're given. Is there a variable by itself? Yeah. What variable right here is by itself? That's a y. Okay. Cool. We've isolated an expression. Technically, they did it for us, but we're done. It's isolated. The second step is to substitute the value or the expression for the variable. Oh my gosh, things are happening. It's not sticking. Substitute the expression for the variable into the other equation. So what I'm going to do, and you're going to do in a second because you're not writing down with me, is you're going to highlight the expression that it's solved for. And where am I going to be substituting or plugging in x plus 3? The y. It says y is this, so then I'm going to take it and I'm going to put it in the equation where the y goes. Okay? So watch. This equation a second ago was x plus 3y equal 5. But now it's going to be x plus 3. And what goes in that parentheses now?
X plus 3.
What I'm substituting in. That's why we're calling this substitution, because I'm taking an expression and I'm going to substitute it in. Step 3 says to solve like normal for the remaining variable, which means I can use the box method or inverse operations to solve this equation. The very first step for either of those two is to distribute. We would have x plus 3 times x, which is 3x, and 3 times 3, which is 9, equal to 5. With the box method, I would start organizing my information so that I could solve. Putting all our like terms on the same side, here comes an x, here comes a 3x. What happens to that 9? Changes sides, so it uses its inverse operation. And now I can combine like terms across the top by adding. This would be 4x equal to negative 4. Still solving like normal. What's the very last step to solve this? By
4.
Cool. So now I got x equal to negative 1. And I celebrate because I'm halfway done. What? Halfway. Think about last time when we gave a solution to a system, did we say one number? How did we give a solution to a system?
2 numbers.
2 numbers, put in a,
Parentheses.
which makes them a. Yeah, no, it puts it in parentheses, but what is that called when we put 2 things in parentheses?
Brackets.
No.
No, it's like on a graph. What is it?
On a graph.
A coordinate.
A coordinate, a plotted point. So these are gotta still be an x and a y that we would find on a graph. Okay, so let's finish. We're on step 4. Step 4 is halfway.
Oh, okay.
Why is this not sticking? This is so annoying. Okay, halfway. We're going to substitute the value or number from step 3 into one of the equations and simplify. Doesn't matter which one you choose. Out of habit, I always pick the top equation to substitute it in for. So that top equation, I'm going to read it off your paper because I can't see mine, is y equal x plus 3.
Yes.
But yeah, I got that right off your paper. You just can't see it up here, but if you look down at yours, it's on your paper. It's the first equation. But instead of x, what can I plug in for x?
-1.
Negative 1. So now I'm just trying to figure out what y is equal to when x is negative 1, and I add 3 to it,
2.
which is 2. Now that I have both an x and y value, all I need to do is write my answer as a coordinate pair, an x comma y. So if I want to do that, what number goes first?
-1.
Negative 1. What number goes second? 2. There's the coordinate pair that represents the solution for this system. If we graphed this, these are the the coordinate of where they would cross. If we took this x and y value and plugged it into the original equation like we did last time, they'd come out to be a true statement. I know a lot just happened and you haven't written any of it down. So what we're going to do is we're going to take a second, and I'll try to get it all to show up for you. This is fun. There we go. I did it. Okay, take a second, write this all down for yourself. As you're doing it, if you're like, Miss Quigley, I do not know where this number came from, flag us down, we'll come help you. We're going to stay here for a few minutes while you write it down. Since we've walked through the steps again, isolate, substitute, solve, substitute again, and then write it as a coordinate pair, I think we're ready to try the second one. So let's find it on the inside. We want to solve this system by substitution. Now the steps aren't here for you to look at, so we have to remember them. The first step was to isolate a variable. Is there a variable isolated here?
Yes.
Is there a variable by itself?
Yes.
Yeah, look at that. X, isn't x equals mean that it's by itself?
Yep.
All right, so x is by itself. We are good. We put a little check mark. We know that it is isolated. Now we're going to take that expression and we're going to substitute it in. So I'm going to take 16 minus 4y. And where am I going to plug it in the second
After
one?
the 3.
After the 3, because it's what variable? The x variable. Oops, that wasn't a very good dot. There, that's better. So instead of the equation being 3x plus 4y equal 8, it's actually going to be 3 parentheses 16 minus 4y plus 4y equal to 8. That's the substitute step. I've replaced the x with the value of x, which is this expression. Okay? Third step is to solve like normal using distribution and then either the box method or inverse operations. We're going to continue. So I'm going to show the box method. But we'll distribute 3 times 16 is 48. 3 times negative 4y is negative 12y. Then I add 4y. Should be equal to 8. Did I lose anyone on that step? No, we see? Okay, from here, box method or inverse operations to finish solving. I'll show the box method. If you like inverse operations, you just go for it. 48 would have to go bloop all the way over here, so it changes signs. Negative 12y does not change signs. 4y does not change signs. And 8 does not change signs. 48 is the only one going across.
Wait, what? You confusing me there.
Where am I confusing?
They only change signs when they cross the sign.
Correct. When they cross from one side of the equation to the other, which is why we draw the line, because it helps visually see it. Now we add across the top, which is combining like terms. This would be negative 8y and negative 40. What's the last step here?
Wait, how'd you get that?
I added. Negative 12 plus 4 is negative 8. And then negative 48 plus 8 is negative 40. I would divide. Thank you. I heard that. And we divide by negative 8. What's negative 40 divided by negative 8?
Positive something.
Positive something. That's correct.
So why did you divide by negative 8?
I divided by negative 8 because I want the y. I'm trying to isolate the y again, get the y by itself essentially. And so we want that negative 8 to go away. When negative 8 and y are smushed together, they're multiplied.
Fine.
So the inverse is to divide.
Okay. Right. If I care.
Yes? Okay. So y is equal to 5. Thank you, Abby. Y is equal to 5. Now that's half my answer. We do a slight happy dance, but really we got to keep going. So what we're going to do is we're going to take that equation or that value that we got, and what are we going to do with the number 5? What are we going to do with the number 5? What are we going to do with the number 5? Plug it into one of the original equations. I always choose the first one because it's generally easier. So this is going to be, instead of x equal to 16 minus 4y, I'm going to write it as 16 minus 4 parentheses 5. 16 minus 4 times 5. Well, 4 times 5, that's 20. So I'm really doing 16 minus 20. And 16 minus 20 Negative 4, but yes. Negative 4. And now I have both the x and the y coordinate for my coordinate pair. What would be my final answer?
It would be -4, 5.
Absolutely. Negative 4, 5 is the ordered pair. That is the solution to that system. If I were to graph these two lines, negative 4, 5 is where they cross. If I were to plug in this x and y value into the original equation, it would come out as true. Join me on number 3. Number 3, again, ask me to solve that system by substitution. What do you notice about this system, though?
They're not separated by themselves.
There's not a single variable by itself. Good observation. So we actually have to do the original step that says isolate the variable. Okay? So up here, since we don't have a variable solved for, it doesn't say x equal or y equal, we have to do it. Now this is a part where you can have an opinion. It does not matter which you choose or which equation you choose. We need to solve for a variable. I'm going to decide that for right now, we're going to solve the first equation for x. When we solve the first equation for x, all we have to do is take this and rewrite it or isolate the x. So instead of x minus y equal to 3, if I was wanting to get the x by itself, what would I have to move?
The Y.
The y. And how do I move that y?
Inverse operation.
What is the inverse operation? Addition. What I do to one side, I have to do to the other. And the y's would eliminate from the left so that I still have the equation x equal to y plus 3. Now, do I have an equation isolated?
Yes.
Yes, I have an equation isolated. So I highlight the isolated expression, and where am I going to plug that in?
Where the X is.
Where the x goes. Very cool. What's up?
Does it matter which equation you choose?
It does not matter which equation you choose. I could have solved the bottom one for y. I could have solved the top one for y. I could have solved the bottom one for x. This is a kind of a creative moment. You get to decide what you want to do. I just happen to choose this one. Now that we have it isolated, and we're going to substitute, instead of x plus y equals 7, that new equation can be written as
X plus Y
x, which is y plus 3, plus y equal to 7. That's the substitute step. Now, the parentheses are kind of useless in this question, to be honest, because is there a number in front of those parentheses? No, there's not even a -1. It's just a straight up 1. So if I were to distribute a 1, nothing would change. So really, we can just write this equation over again as y plus 3 plus y equals 7. Do y'all mind if we use not the box method to solve this one? Yeah. If you like the box method, please go ahead. But what I'm going to do is I'm going to combine like terms first. How many y's do I have?
2.
2. So I have 2 y's plus 3 equal to 7. What am I going to subtract from both sides to start getting the y by itself? I'm doing the inverse operations method. If you're doing box method, we'll catch up at the final answer.
Oh, wait, yeah.
We divide by 2 on both sides. So either way, if you're doing the box method on your paper or you followed along with my inverse operations method, we should have ended up with y equal to 2. A halfway happy dance, because that is only halfway through the question.
And then you do division.
Oh, the other.
That is
It's halfway, but now that I have half of the solution, all I have to do is plug it back in and solve again. This time, I'm going to be plugging x equal y plus 3, but instead of y, it'll be a 2.
So 2 plus 3.
which is just 5.
And then you put it in the word
We do put it in a coordinate. Which one goes first?
5.
5, comma, 2. That is the coordinate of the solution. Again, if we were to graph these, that would be where these two lines crossed. If we were to plug in this x and the y back into both equations and check to see if it's correct, just like we did last class, it would be correct. What was your question? Woo! These problems are longer. Okay, they're not hard, they're just a little bit longer, it takes a little bit more stamina. If you would please find the elimination section of your notes, which is the other piece of paper that you have when you picked up when you walked in. No. Okay. What do you hear, or what do you think about when you hear the word eliminate?
Take away.
Take away, maybe
Subtract.
subtract. Get rid of. I like get rid of. Get rid of or cross out. Not ignore. We actually have to get rid of them or cross them out. Now, we are going to be eliminating variables here, eliminating terms to make our solutions appear for us. To get an elimination problem to happen, what we need to find is called opposite-like terms, which opposite-like terms are simply the positive and negative of a term. So whatever you have in front of the x, if you have the opposite, those are called opposite-like terms. So, for example, what's the opposite-like term of 3?
-3.
Negative 3. What's the opposite-like term of y?
Negative y.
Negative y. Just the positive and negative version. What's the opposite-like term of negative 7x?
Positive 7.
Positive 7x. We need to be able to identify opposite-like terms to be able to do elimination. The other thing we're going to have to be able to do, and the more complicated aspect of elimination, is called a scalar multiple. Have y'all ever heard of a scalar multiple?
No.
When you learn about geometry, I think you did this in 8th grade, but it might be a high school geometry, so in a couple years. You might take a shape like a triangle on a coordinate grid and multiply it by a scalar multiple, which makes the entire thing bigger. So not just one side getting multiplied, but like all 3 sides get multiplied. That's kind of the same idea, because a scalar multiple in algebra is simply just distribution over the entire equation, which includes both sides of the equal sign. It feels like you shouldn't be able to do this. This feels like an illegal math move, but you're actually totally allowed to do this. It's called scalar multiplication. An example of scalar multiplication is here for you. I want you to multiply the equation 2x minus 5y equals 3 by the scalar multiple of negative 3. It feels illegal, but it's totally legal. What we are going to do is we're going to take the equation 2x minus 5y equal to 3, put the whole thing into some parentheses, and multiply the whole thing by negative 3.
Wait, that's all you do?
Yeah, it feels wrong because you're going to multiply the first one. Negative 3 times 2x, negative 6x. And negative 3 times negative 5y,
Positive 15y?
positive 15y. And negative 3 times 3.
Nah, negative 9.
So I have equals negative 9. It goes on both sides of the equal sign, which feels weird because normally you're not allowed to do things like that. But a scalar multiple, you're allowed to multiple all pieces of the equation by that number. Yeah? So we're going to do elimination kind of the way we started with substitution, where I'm going to work an entire problem out for you without you writing down with me. And then I'll stop and let you copy it all down. But you'll miss something if you try to write, listen in, and look up and look down all at the same time. So I just want you to watch with your pencil and highlighter down. You will pick it all back up and be able to write it down in a second. Okay? The steps to solve an elimination question are as follows. We need to know that these equations are written in standard form, which is alphabetical order. So if we look at both of ours, you see how it's x, y number, I'm good. That's standard form. I need to find an opposite-like term, which means I'm looking for one variable in the top and the bottom to be opposite-like terms. And if there's not, that's when I have to use my scalar multiple, which is not going to happen on this question, but we will do it on a couple others today, okay? So if we look at my equations, do you notice that right here with my x's, they are opposite like terms? One of them is positive 1x, the other one is negative 1x. Do y'all see that? That's an opposite like term. I'm good to go. Step 1 is done. Step 2 says to add the two equations together. Again, this feels a little bit illegal, but you're totally allowed to do this. You're going to make an old-fashioned elementary school addition problem. Bloop, bloop. Straight up add the equations together. When I add these equations together, I combine the like terms, which means positive x and negative x cancel each other out. They eliminate. We got rid of them. We cross them out. That's elimination. But I keep adding, so 3y plus 2y, that's 5y. 17 plus 8, that's 25. I'm already done with that second step. The next one says to solve like normal. There's only one step it takes to solve like normal. Divide by 5.
Okay, so 5.
I'm already halfway done. Woot woot. Okay, I have now half of my answer. I have the y value, and I need to find the x. The second half of this, I keep drawing this big old purple line on here. It's because that's like the first half and the second half. The second half is essentially the exact same as substitution. In fact, it's literally copy-paste of step 4 and 5 from substitution. It says to substitute the value from step 3 into the either equation and simplify or solve like normal. So I'm going to take the top one because, again, that's my habit to take the top one. And instead of x plus 3y equals 17, I can write x plus 3 parentheses 5 equals 17. Where did I get the 5 from again?
Your y.
My y. That's what I solved for the y part. Then I just solve like normal. This would be x plus 15 equal to 17. And what do I have to add to 15 to get 17?
2.
2. Because inverse operations, x would be equal to 2. Now, very last step yet again is to write our answer as a coordinate pair. So what is the coordinate pair answer for this equation?
2y. 2, 5.
2, 5. Very good. That's the x and y values for this elimination system. You're totally allowed to have an opinion on which one you like, but go ahead and write this one down. That way you have it on your notes. Okay, I'll walk through the steps one more time with you just to make sure now that you have it all written down, you know what you wrote down. So we started off by making sure that our equations that we were given in the system is in standard form. XY number, we're good. We then look for an opposite like term. The x's are opposite like terms because this is positive 1x and this is negative 1x. So I circled them. Step 2 said to add these equations together, and when I do that, I eliminate one of the variables. That's what I wanted to have happen. That's why it's called elimination. Okay, 3 plus 2 is 5, 17 plus 8 is 25, and I solve for y. Then I take the value for y and I substitute it back into either of the two original equations. I could have chosen the second one, I just didn't. I chose the top one. And I eventually solve for the x. Then I write my answer as a coordinate pair, x, y. Do we feel ready to try one together?
Yes.
Cool. Open up this little notebook to the inside, and pretty sure some people have already noticed the problem with this one. What's the issue with question number 2?
You don't have opposite like terms.
It does have a 0, but that's not what's the problem. What's the problem?
Opposite like terms.
Are there opposite like terms?
No.
No, if we look at the x's, we've got 20 and negative 10. Are those opposite like terms?
No.
We've got negative 10 and 2. Are those opposite like terms? No. So here's the kind of question that we have to use a scalar multiple for. We need to multiply one of these equations by a number to get them to become opposite like terms. I want to either make the x's opposite like terms or the y's opposite like terms. Doesn't matter which one, because either will work. But let's try the x's. What does this number need to be for these to be opposite like 10?
Negative 20.
This needs to be negative 20 for these to be opposite like terms, because this is positive 20, so this needs to be negative 20. So what would I multiply this by to get that to happen? 2. My scalar multiple for this question is 2. So I'm going to take a 2, and I'm going to multiply it by the whole equation. My recommendation is that you rewrite the entire problem whenever you have to do this, because otherwise you won't know what numbers you're using. So did we change anything about the first equation? No, so we just go ahead and write it down. 20x minus 10y equal to 0. But we did change the second one.
Yes.
2 times negative 10 is negative 20x. 2 times negative 2y.
Negative 4y.
And 2 times negative 14.
Negative 28.
Negative 28. I did use a scalar multiple here. But now, do you notice that there is an opposite like term?
Yes.
Awesome. We're now done with step 1. So sometimes it's not done for you. You're going to have to figure out the number that you have to use there. That's the thinky part. Second step told me to add the equations together, like an old-fashioned problem. What happens when we add together these two equations?
They cancel each other out.
What cancels each other out?
The 20x and negative 20x.
The 20x and the negative 20x. Those are opposite like terms. It's gone. Bye. Then I keep adding. Negative 10 plus negative 4.
Is negative 14.
Negative 14y.
Equals
0 plus negative 28.
negative 28.
Type.
And
That's
then solve.
That's the eliminate step. We are going to solve. What's the one step in elimination it takes to finish solving?
You divide. Well, yeah.
Mm-hmm.
Negative 14 is solved.
Then I'd have y equal to, what is negative 28 divided by negative 14?
2. Right.
Mm-hmm. 1 second happy dance because we are done with half of it, but we have to keep going.
Now we got to do the other half.
Part 2.
20x.
What do I do with part 2?
You write down the problem and then insert it.
Yeah, I'm going to write down one of the original equations, usually one that you haven't used a scalar multiple for. That's just a good habit. I always pick the top one no matter what, but like that's just my habit. And instead of writing 20x minus 10y equals 0, I can write, oh, I should be using purple. 20x minus 10 times, what goes in there for y?
2
2
equals 0,
equal to 0.
which is 20x minus 20 equals 0.
Negative 10 times 2 is negative 20.
Which is a true equation. And now we have to solve under.
Solve for x. You can either use the box method or inverse operations. Box method is a lot more work actually in this aspect because we're just going to add 20 to both sides. This would be 20x equal to 20.
Oh, okay.
Divide by 20 on both sides.
Which is
So x would be equal to
1.
20 over 20 is 1. It reduces to 1. So what's my final coordinate here?
1. So it'll be 1, 2.
1, comma 2 is my coordinate of the solution. If this were a graphing systems equation, this would be the coordinate where they meet. If it were something where we were checking the work, we'd plug those two things in and see if it comes out to a true statement. Comments?
You don't have to do
Come on, the comments.
It's easy.
Okay. Let's look at number 3. What do you notice about number 3?
that you have 2 opposite like terms.
Does anyone else notice that? You have 2 sets of opposite like terms.
It's 3, 3, 3.
If you notice on number 3, the x terms are opposite like terms. The y terms are opposite like terms. So I'm actually going to circle both of these when I'm identifying my opposite like terms. I only need one to continue. So once I've identified at least one of them, I can do the next step, which is to add the equations together. When you add these together, what happens to the opposite like terms?
They cancel each other out.
They eliminate, they cancel out. So, oh snap, is there anything left on that side?
Yes, well, yes and no. You have to add 28.
Oh, I mean on the left side.
No.
No, so what number does represents nothing's left over there? 0. And then I keep adding, so 8 plus 20 is 28. What's weird about what we just wrote down?
It's not a true. Well,
Yeah.
you don't have a variable.
I don't have variables anymore, and does 0 equal 28? No. If this is a false statement, wait, say it again. This is no solution. If I have my variables cancel out, and I'm left with a not true statement, if I'm left with a false statement, then there is no solution to this system. Bonus question, show me with your arms, what would this system look like? I see it from some people. What would a no solution system look like? Very cool. I love it. Great. Nice arm motions. This is what this system would look like. Pretend those are straight lines that never touch. This is a parallel system. They have no solution. Let's check out number 4.
No solution.
Again.
All right, what's wrong with number 4?
No opposite like terms.
There's not no opposite like terms, right? 2 and 6 are not opposite. -6 and -18 are not opposite. So we have to do something about it. Right now think, don't say it out loud. What would we multiply one of these equations by to get them to match? Don't say it out loud, just think it. They need to be opposite like terms. What could I multiply one of the equations in number 4 to get them to be opposite like terms? We can multiply them by, well, let's do less work. We could multiply both of them by something, but let's multiply one of them. What are you thinking?
-3, the top one.
If we multiply the top one by -3, is that going to work? Well, let's think about it. If we're trying to get, were you trying to get the x's to cancel out? But if we're trying to get the x's to cancel out, we could have tried the y's. This needs to be what number?
-6.
It doesn't need to be 2. It needs to be -6. What would I have to multiply 2 by to make it -6?
-3.
-3. So that means my scalar multiple is going to be -3. Great job. Because when I multiply all of those by -3, this would be -6x plus 18y. Here's where I'm getting this, by the way. Equals 6. Okay, since I didn't change the second one, I'm just going to rewrite it down again. What do you notice now about your system?
They're all opposite like terms.
So, yes, what did you say? Are you sure? I just like literally didn't hear you. When we have some variables that are what? What is this called? Opposite like terms. But what is also an opposite like term here?
The numbers.
What happens now if I were to add all of these together?
0 equals 0.
Cancel, cancel, cancel. And what did you just say?
0, no solution.
They all become 0.
Well, 0 equals 0, so there is a solution.
So it's a solution.
What is the solution then?
Infinitely
many solutions. Yeah. IMS. Because this is a true statement, my friends. We will say IMS, infinitely many solutions, as the answer here. Bonus, show me your arms. What does an infinitely many solutions graph look like? We're all struggling to do it. Yeah, it's the one where your arms are right on top of each other. If you have like a nice stiff jacket on like me today, you like literally can't get your arms there. But yes, infinitely many solutions. These are the same line. They would look like they're right on top of each other. It would look like the first line was graphed, and then the second line came on right on top of it. And infinitely many solutions. So there's a possibility that when you solve elimination and substitution questions, you could still get one of the special cases. So you've got to be ready for those.